In an emergency like this, measurement can play a vital part.
Okay.
See how many measurements you can spot.
Let's check his eyes, Liz.
Some you can estimate just by looking. Observing how the eye reacts to a light can tell you how conscious the patient is.
What's your name?
Okay.
Keep nice and still, Nick, will you? Is there any pain?
Yeah.
All right, Nick, we'll have a look at it. Keep it still, and we'll look at it. Just going to take your pulse.
But most measurements are made more exactly with the help of an instrument. The ambulance man uses his watch to time the pulse rate. Inside the ambulance, there are other measurements to take.
All right, Nick, you're in the ambulance now.
This instrument measures blood pressure.
Now then, Nicholas, I'm just going to take your blood pressure, and you can help me here. Can you get your good arm out of the blanket? Mind your bad one, won't you? And keep it out nice and straight, and I'll just roll your sleeve up, okay? They're good strong arms, aren't they? Now I'm just going to slip this cuff over your arm, all right? And put my microphone on your elbow like that, okay? Now then, just blowing it up and you'll feel it come up hard around your arm, but it won't hurt you.
He's finding out how hard the heart is working, pumping blood round the body. These measurements provide a record of Nicky's condition just after the accident.
What have you got? Blood pressure's 90 over 50, pulse rate 120.
And it's vital to write them down.
Okay.
The police make measurements too. This policeman is measuring the length of the skid marks left by the car. That will tell him the distance the car took to stop. He's trying to find out if the car was being driven too fast. To do that, he uses the police car. On the side of the car, there's a chalk gun attached near the front wheel and connected to the brake pedal. He drives the police car at 30 miles an hour, the speed limit for this road, and then brakes. The spot where he braked is marked by the chalk gun. So now he can measure the length of these skid marks and compare them with those from the accident.
15.4.
The result tells him that the car involved in the accident was being driven faster than the speed limit. At the hospital, the ambulance crew are able to report on Nicky's progress from the measurements they've taken.
Hello, Nicholas. If you'd like to take him to room C, please.
Hi, sister.
Hello.
This is Nicholas then. He was knocked unconscious initially, having hit his head on the curb.
Right.
He's regained consciousness after about 5 minutes, and he's had a good blood pressure improvement, and his pulse rate's come down very well indeed. Thanks very much,
Thanks
sister.
very much.
See you in half an hour.
Bye. Now, I'm just going to take your pulse, all right? So if you give me your arm there, that's it. Just nice and quiet for a minute.
The sister takes the measurements again.
That's the pulse, 80.
Each one is noted down.
I'm going to put this band around your arm, and it gets a little bit tight, and I'll listen to your pulse with the stethoscope there, okay? So we just wind that round there. Just feel a bit tight, okay?
Some of the instruments she uses may look a bit different, but they do the same job, like this one measuring blood pressure.
Right, that's 120/70. So that, again, that's better as well. Good, that's all fine, okay?
All the measurements from the time of the accident can now be compared. It's the only way they know whether Nikki's getting better or not.
That would be 5, and they were both reacting, so that's fine.
A record is vital for the doctor.
His observations,
Yes, his
how have they been?
pulse was 80, blood pressure 120/70, pupils both equal and reacting, and everything else was fine.
Fine, and he's improving rather than
Yes,
deteriorating.
definitely.
That's good. Someone will go to X-ray with him just to keep the observations going.
Fine.
Routine observations or measurements are a way of keeping check on a patient's condition in hospital. Temperature is one of the more important measurements. The nurse knows what the normal body temperature should be.
That's fine.
So by recording these measurements on a chart, she can see how this patient's temperature compares with the normal.
Your temperature's gone down again.
Weather scientists or meteorologists also measure temperature. They keep a record of how the temperature of the air changes. It's a routine part of their job too, and it helps them to forecast the weather. But whether you're a meteorologist or a hospital doctor, measurements of temperature only make sense if you have numbers and some sort of scale.
Hello, tomorrow England is going to be warmer. Warmer than today, that is. But that wasn't very warm today, was it? So it might not be all that very warm at all. Wales, on the other hand, is going to be colder tomorrow. Not colder than today, but colder than the long-term average for this time of year. So I suppose it could even be a little bit warmer than England. Scotland, here, colder again, but colder than England and Wales. Mind you, it almost always is, on average at least, colder than England and Wales. So this isn't really telling us very much. It's easier, I think, over Northern Ireland. Here, normal temperatures tomorrow, colder than England and Wales, just a bit warmer than Scotland there. So pick the bones out of that if you can. Let's have a look at Europe, I think, tomorrow. Well, everywhere over Europe, normal weather, but my goodness, that covers a lot of ground, all the way from snow showers up in Lapland, even some snow flurries on the Alps, to sunshine elsewhere, and baking droughts down over the North African deserts. I wish we had some numbers to try to describe the range of temperatures that we're going to get tomorrow, but it's all going to be absolutely normal. Well, of course, we've got numbers now. This is the sort of thermometer that's used up and down the country to measure the temperature. The temperature here in the Science Museum, a very pleasant 23 Celsius. But it was a long time getting there. I suppose we've always been interested in how hot it was or how cold it was, but it wasn't until about 2,000 years ago that we started trying to measure this. In fact, it was a Greek chap called Philo who devised one of these instruments here. We call this a thermoscope. Let me tell you how it worked. The air inside this lead sphere expands as it gets warmer, and as it does so, it forces water into this glass flask, and the level of the water, of course, rises as it gets warmer. And as it gets cooler, the reverse happens, of course. The air inside the lead bulb contracts, shrinks, and sucks the water up the tube, and thereby lowers the level of the water in the flask. But of course, it was open to the atmosphere, so anything could happen. The water could evaporate, so it was really very crude indeed. The first true thermometer didn't come along until very much later, about 300 years ago. An Italian gentleman called Ferdinand II, he was the Grand Duke of Tuscany, right as a button, he devised the first true thermometer. This was a sealed glass tube with liquid inside, and the movement of the liquid along the tube measured how hot or how cold it was. Then I think came the difficult part really, devising marks, the positional marks along this tube so that you could compare temperatures in one place with another. Now to devise a temperature scale, you've got to have a top and a bottom, you've got to have fixed points on that scale. And the scientists had lots of ideas for those. One of the points they thought would be the temperatures of deep caves below the ground. They're very low down there, it's really pretty cold. For the top of the scale, one of the suggestions was the temperature of the human body. We're pretty warm and pretty constant too. But finally, they settled on a top and a bottom. At the top was going to be the boiling point of water, that's pretty constant, and the bottom was going to be the melting point of ice, that's pretty constant too. And they were going to divide the bit between the two into various numbers so that they could compare. Of course, every scientist in those days devised his own temperature scale. There was a Frenchman called Réaumur. He had to be different, of course. His bottom was 0, his top was 80. And then there was another one called Fahrenheit. His bottom was 32, and the top of his scale was 212. And then, more recently, Celsius, the same as the centigrade scale, the bottom was 0, the top was 100, we all use that now, that's one of his thermometers just there. Wouldn't it be very confusing if we used all those temperature scales in the weather forecast? Hello. In Southampton tomorrow the temperature will rise to 10. That's 10 degrees Celsius or centigrade, it's the same scale really. But up in Falkirk the temperature will soar to 46. But 46 degrees Fahrenheit, so that's just a little bit colder than Southampton. At the same time, Ruislip tomorrow will get up to 9. But that's 9 degrees on the Réaumur temperature scale, so it is actually a bit warmer than either of them. But I'm really worried about Aberdeen. Here tomorrow the temperature's only going to get up to 280, but that's 280 degrees absolute, so that really isn't all that warm at all. And Cambridge too, the coldest of the lot, rising to 279 degrees on the Kelvin scale, which is just the same as the absolute scale. There are more temperature scales, but it's getting confusing enough. I think I'll stay in bed.
Nowadays, nearly everyone uses the Celsius scale, and temperature measurements are all standardized. But how do the meteorologists know they can rely on their thermometers to agree with each other? Well, they're checked. That's what this scientist at the British Standards Institute is doing. The thermometers are immersed in a bath of warm water. She's comparing their measurements with the measurement given on the white thermometer at the end. The white thermometer is special. It's known as a working standard thermometer. But how do scientists know that they can rely on the measurements of a working standard thermometer? Each one is checked against a very sensitive device that measures temperature electrically. It's called a resistance thermometer. And this resistance thermometer is checked in its turn at the National Physical Laboratory. It's set, or calibrated, against the temperature of something in nature that never changes, a known fixed point. The most important one is when water, ice, and water vapor exist together. It's called the triple point of water. It's an agreed fixed temperature point all over the world. With this resistance thermometer, measurements appear as units of electrical resistance, and with the help of a calculator, the scientist can get a reading of temperature. The reading should be 0.01 degrees Celsius, and this thermometer is close enough to pass. There are other fixed points at higher temperatures that thermometers can be compared with. Here, the scientist is going to heat up a small amount of the metal zinc in a lead crucible. It's heated in a kiln until it melts and is then left to cool. As it cools, the molten zinc turns back to solid. The temperature at which zinc turns from liquid to solid is always the same. It's another fixed point against which this kind of thermometer can be checked. So, by comparing thermometers against fixed points, you know that wherever and whenever they're used to measure temperature, they'll always agree with each other. The fixed points provide a standard for the measurement of temperature. There are standards for all forms of measurement, like length. These are working standard meter bars, and they're compared with the length of something in nature that's always the same, the wavelength of a particular kind of light. The comparison is done at the National Physical Laboratory in a light-proof, airtight box in which conditions can be carefully controlled. By comparing all the working standards of length against just one reference standard, scientists know their measurements of length will all agree. There's also a standard for time. You probably know it as Greenwich Mean Time. The standard second is the time interval between the start of each of these bleeps. You can hear them on the radio at certain times of day. Inside the clock are atoms of cesium, which are vibrating very, very rapidly. It's the precise number of these vibrations, millions of them, that gives us the standard second. And this is our national standard for mass. It's a chunk of metal, Britain's national standard kilogram, number 18 in the world. Scientists use this national standard to check the working standard kilograms. The comparisons are done on one of the most sensitive balances made, so sensitive it has to be enclosed in an airtight cover. The balance is controlled remotely, and any difference in mass is calculated from the movements of the light beam reflected off the balance. In the case of the kilogram, there's even an international standard. It's kept at a laboratory near Paris, and every country's reference standard kilogram is compared with this one. This method of checking by comparison means that wherever and whenever you buy a kilo of whatever, you know you're not being cheated.
Bonjour madame, un kilo de cerises s'il vous plaît.
Oui.
Buongiorno.
Mi dà un chilo di queste?
Bonjour, un kilo de pommes s'il vous plaît.
Un kilo de pommes. Lesquelles je vous mets?
C'est là.
Un kilo.
Quisiera un kilo de chorizo y 200 gramos de queso de cabra.